Yes, welcome. This is 300 Plus Academy, where all we do is exams, tutoring, still on the subject chemistry, but this time around we're trying to look at the properties of matter as well as physical and chemical changes. It is part of your syllabus, and we have no option other than to treat that particular topic. Okay, talking about the properties of matter, the properties of matter can be physical and can be chemical. That is, if we are trying to look at things from the perspective of if we are making reference to other substances or not. Talking about physical properties are properties that can be specified without making reference to other substances. Take, for example, the color of a material. I can't, it doesn't make sense for me to say, for me to get the color of a certain material, I'll need to add this, then I'll need to, okay, let's say add an acid to a substance for me to tell the color, for me to tell the odor. No, the color is something I can specify without having to talk about other substances. Take, for example, odor is another one. The odor of a matter is its odor. The odor is not something I get because based on if I've added other substances. No, the odor is the odor. The taste is the taste. The density, that's the mass per unit volume, is the mass per unit volume. Talking about physical properties, I do not need to make reference to other substances. But talking about chemical properties, you have to make reference to other substances. You cannot specify without making reference to other substances. So what that invariably means is that for you to tell the chemical properties of a substance, you have to make reference. Take, for example, if you want to talk about the reactivity of a material, or let's say an element in this case, you must, for you to tell me it's reactive, you must have, okay, brought other substances in contact with it. You must have brought an acid in contact with it. So you must have brought different things in contact with it. So you make reference to other substances to tell the activity. If you want to know if something burns or undergoes combustion, of course you must have added oxygen to that substance. So the fact that I have to make reference to other substances makes defines chemical properties. If you have to make reference to other substances, then that's the chemical properties. If you don't have to make reference to other substances, then that is physical properties. Also, we may look at the properties of matter based on the size of sample of materials. Okay, extensive property depends on the size of the sample. Like the more the mass, the more the size, then the more this particular properties. Extensive, like you can see from the word extend. Take, for instance, the mass of a material. Let's say, okay, this is the mass of this, this is the mass of this. Because the size of the sample are changed, you expect the mass to change. So talking about extensive properties, it depends on the size of sample of matter. You talk about volume, look at the spaces occupied, look at the spaces occupied. So that is that about that. When you talk about extensive properties, you it depends on the size of the sample of matter. Mass and volume is an example. Intensive properties, on the other hand, has nothing to do with the size of the sample of the material you are dealing with. Take, for example, it doesn't matter the size of the material, the color is the color. The color is the color. You cannot say because the size had increased, then the color will change. No, the odor remains the odor, the boiling point remains the boiling point, and the density remains the density. Let's quickly talk about physical and chemical changes. So that ends extensive and intensive properties of matter. Moving on, the next thing is to talk about physical and chemical changes. When we say physical changes of matter, physical changes are usually temporary changes which can be reversed. We call they are temporary, they can be reversed, new substances are not formed. Take a look at the case of ice. Ice, if we eat, it could melt, it becomes water. If we eat, the water could undergo evaporation or vaporization and become steam. But at the same time, we could reverse that process such that if we liquefy or condense steam, steam could become water. And then if we freeze water, if we bring down the temperature or we remove it, the water could then return back to ice. So that's an example of a physical changes, and that was why I said here, change of state of matter. All of the change of state of matter from melting to evaporation to condensation to freezing to sublimation are all physical changes, simply because the processes can be reversed. Those processes are temporary, and at the end of the day, new substances are not formed. Imagine here we started with ice, we moved down to steam, we could come back to ice from steam, that's from the gaseous state. So when you talk physical changes, they are usually temporary, and they can be reversed, and new substances are not formed. Now, what only happens during a physical change is that the arrangement of the molecules, the arrangement of the particles is what is altered. The arrangement of the particles is what is altered, like from solid here to water here. Here the particles are packed together and held together by strong intermolecular forces, but for water, the cohesive force, the intermolecular force, is not as strong as what you have in solid, in ice. And then in steam, the particles are even more spaced out, such that the cohesive force there is negligible. So what are we saying here is that physical changes are temporary changes, they cannot be reversed, and new substances are not formed at the end of the process. What is only happening here is that the arrangement of the molecules are being altered, are leading to a change of state. So what only happens during a physical change is more or less of a change of state. Also, think about it. The energy needed to bring about the physical change is equal to the amount of energy required to reverse the change. The energy you will use in converting ice to water here is the same amount of energy you will need to remove for you to make sure that freezing or solidification happens. If I will need 50 joules, if I will need to add 50 joules to make ice become water, for example, then I would also need to remove 50 joules from this to make water return back to ice, so that at the end of the day, there is no net energy change. The energy you use in causing the change is the same energy you use in reversing the change. So in that case, we say no energy change. That's what I'm trying to say here. I said the energy needed to bring about a physical change. That's a very important point. In fact, that's more or less of a jam question. The energy needed to bring about a physical change is equal to the amount of energy required to reverse the change. Thus, there is no change in energy. That is, no energy changes occur. Take for instance again, the energy you will need in converting water to steam, that's via evaporation, is the same amount of energy. For you to reverse it, you will need the same amount of energy for you to convert steam to water. So when you look at it, no energy change. Energy you use for the forward is what you use for the reverse. So no net energy changes. Also, you need to know that the mass of the substance remains the same. If this is a 30 gram, this will also be 30 gram. The mass of the substance remains the same. Mass is not involved in a physical change. It is not about addition or subtraction of masses. No, masses are not involved. All that happens here is just arrangement of molecules. So physical changes are temporary and cannot be reversed. Examples of physical change, the first one I said, dissolution of salt in water. The solution of salt in water. Let's look at it. Let's say this is salt, and I'm adding this salt to water, so that what I'm going to have is a salt solution. Sure. What I'm going to add is a salt solution. Now, I could actually pick on the salt solution. I could pick the salt solution to reverse the process. How? If I eat, I could drive out the water by evaporation. I could remove H2O by evaporation if I eat. If I drive out the water from the solution, I could then condense it later and get back my water. So what I'll be left with is going to be my salt. And then if I condense my water, I get back my water. So you look at it, it is not a chemical change, it is a physical change. All of the change of state of matter, they are all physical change. Also, eating of zinc oxide. Zinc oxide normally is white. When you eat zinc oxide, what it does is that it changes to yellow color. It suddenly becomes yellow. But when you then allow it to cool, it changes back to the white color. So you see, there is no net change here. There is no net change here. It's just about the color change here. If you eat zinc oxide, it will change to yellow when hot. When you allow it to cool, it is going to change back to its actual white color. And then another physical change is magnetization and demagnetization of iron. We could make iron, we could turn iron via contact process electrical method into becoming an iron, and we could also make that magnet turn back to iron. That's, we could demagnetize it. So magnetization and demagnetization of iron are physical changes. Okay, moving on to chemical changes. Chemical changes are permanent changes which we cannot reverse, cannot be reversed. They cannot be reversed. That is, they are irreversible, and in which new substances are formed. I will use the case of firewood, burning of firewood. Let's say we have firewood now. Firewood, as far as chemistry is concerned, is more like carbon. It's more like carbon. So if we burn this, to burn this means oxygen is now added. To burn this means oxygen is now added, because usually when we say burning in chemistry, it means oxygen is combining with something. It's the same thing as saying combustion. So in this case, what will be formed? You're going to be left with ash, and you're going to be left with ash, and gases will be liberated. In this case, those gases will be carbon dioxide. In the case of carbon dioxide will be formed if or carbon monoxide. Let's say the firewood is carbon plus oxygen. Okay, carbon plus oxygen will give me carbon dioxide. This is the case if there is plentiful or unlimited supply of oxygen. But in a case where I have limited or short supply of oxygen, what will be formed is going to be carbon dioxide. What will be formed is going to be carbon dioxide. That's limited oxygen supply. Limited oxygen supply. So that is it. When we say firewood to burn, that means carbon there is reacting with oxygen. We're going to have ash, and this gas evolved or liberated. Now the question is, can we combine the ash and the carbon dioxide? Can we combine the leftover and the carbon dioxide or the carbon monoxide to get back our firewood? We cannot do that. So you see that the process is not reversible, and that's what we mean by chemical changes are permanent changes which cannot be reversed, and in which new substances are formed. In this case, a new substance is formed. That's the ash and the gas liberated. Take note, when there is plentiful supply of air or oxygen, then carbon dioxide will be formed, CO2. When there is limited supply of air or oxygen, then carbon dioxide will be formed. Talking about chemical change, it is a change in which the molecular composition is completely altered. And that's what happens here. We add carbon, and what we had at the end was carbon dioxide. we have firewood, we ended up with ash. The composition is totally altered, so that's what makes it that a new substance, a new product is formed, and there is nothing you can do to those products. You cannot reverse them back to the reactant. The mass of the substance, even when you weigh what you have at the end of the reaction as compared to what you have initially, there will usually be differences in mass. Either the mass is now more or the mass is now less. So what we basically say here is that the mass of substance is altered during a chemical change. Either the mass is added or removed. See, what you have as leftover, the ash and the carbon dioxide, if you weigh them together, it cannot be the same as the firewood. So that's what we mean. In the case of physical change, there is no mass change. When you weigh what you have before, what you have after, it's the same. But in the case of a chemical change, there is a change in mass. Either mass is added or removed. Now, also, energy changes occur. There is an energy difference in the breaking of bonds. Take, for example, for the firewood, the carbon is solid. Now, this is oxygen gas. And then we ended up with carbon dioxide, just ash and carbon dioxide. When you check the energy content of the product and of the reactant, they are usually not the same. There is a change in energy here. Because why? The molecular composition is completely altered and new substances form. So what we have here is that there is a change in energy. Energy changes occur. There is an energy difference in the breaking of bonds in the reactant and formation of new bonds in the products. So we say here that there is energy change. Let's look at examples of chemical change. Burning of wood, which gives white ash, and carbon dioxide. That's the first thing I said there. There is nothing you can do to react your ash with your carbon dioxide. You cannot get your firewood. So burning is actually a chemical change. Another one is souring of milk. When your milk turns sour, there is nothing you can do to get things back, maybe due to fermentation or what have you. Once it turns sour, you cannot reverse the process. Another one is dissolution of metals in acid. You know, dissolution of metals in acid. Whenever metals dissolve in an acid, hydrogen gas is liberated most times. Take for example, let's say I have zinc. Zinc is a solid being dissolved in dilute sulfuric acid H2SO4. Okay, aqueous. Now, this is what I'm going to have: zinc sulfate aqueous plus hydrogen gas is liberated. I could say, okay, let me talk about, let's say, magnesium plus hydrochloric acid. Okay, what am I going to have to balance this? For the record, this is magnesium chloride plus hydrogen gas. This is a chemical change because you cannot combine the gas with the aqueous solution. You cannot combine the gas with the aqueous solution to get back your reactant. And that's what we mean. When you look at the energy content, the energy of the product and the reactant, there are a marked difference. This is solid and aqueous. Now this is aqueous and gas. This is telling me that the heat of the product here, heat of product, is more than the heat of the reactant, and that's why we say heat changes are involved in the cause of chemical changes. So dissolution of metals in acid is actually a chemical change. Another one, dissolution of limestone or marble chips. Yes, limestone or marble chip. That's calcium triisocarbonate 4 in acid. Imagine in the production of carbon dioxide, calcium carbonate. This is solid. Marble chips or limestone, that's the name we give out to it. Okay, dissolve in an acid. This is what we're going to have: calcium, then this is chlorine. Calcium has 2 in its outermost shell, chlorine has 7. Of course, when I teach you about octet duplet rule, from that point I will begin to try to balance the equation. But in this case, the right thing here is calcium chloride. Okay, calcium chloride, and then you have water and then you have your carbon peroxide gas liberated. You see, when you look at the heat of the product and the heat of the reactant, there are marked energy change, and that's what makes this a chemical change. You cannot reverse this process. The product you have is totally different from your reactant. You cannot reverse the process, and that's what makes it a chemical change. Another one is the burning or charring of sugar. When you burn your white sugar, okay, the sugar at this point is white. When you eat, what you're going to have left is a black residue, which you call black sugar. The sugar loses its crystalline structure, because now the water of crystallization that gives the sugar its characteristic crystal color is now out as steam. Yes, is now out as steam. So there is no way you can combine the steam with the black remnant, the black residue, to get back your sugar. So burning or charring of sugar is actually a chemical change. Another one which is very important is rusting of iron. When we talk about corrosion talks generally about how metal deteriorates when exposed to air and moisture, and that oxidizes them, causing their corrosion. But rusting is the name we use specifically for deterioration of iron. Rusting of iron in the presence of oxygen and moisture. Okay, let this be iron, Fe, that's solid. Okay, in the presence of air, that's oxygen. Let's use oxygen here, oxygen gas in air, and moisture. Let's talk about water. Okay, when we have this, we need to understand that this is more or less, if oxygen and water, and if they are to attack this iron, of course, oxygen being a gas or air could move more. So this is seemingly going to look like a reaction between iron and oxygen. And whenever iron reacts with oxygen, it is the lower oxide that is going to be formed there, Fe2O3. I'll need to balance this because I have 2 oxygen here. This becomes 3, okay? And, oh, sorry, that means this will be 2. If Fe2O3, iron 3 oxide, in balancing this becomes 4. And of course, I have water here. Okay, this is going to be dot H2O. I don't know the amount of water. I could leave it as dot H2O if I want. So which means, okay, these two could cover for everything, but it could be more than that. So I could say 2x, or I could just say x, so that the 2 covers for this, and this is for water. This is brown hydrated iron 3 oxide, and that is the formula for rust. Don't forget that is the formula for rust. That is a JAMB question. The formula for rust is brown hydrated iron 3 oxide. That is the formula for rust, whereby iron combines with oxygen and moisture, giving us Fe2O3, H2O, hydrated brown iron 3 oxide. That is rust. You see this rust now, there is nothing we can do to reverse the process. It is not possible. Once the iron turns brown, it turns brown. Once this compound is from brown hydrated iron 3 oxide, there is nothing you can do to reverse it so that you get back your oxygen. So rusting of iron is actually a chemical change. The next, another chemical change is fermentation and decay of substances. Of course, when we talk about fermentation, let's talk about fermentation. Fermentation is the conversion of glucose into alcohol. Usually, anaerobic microorganisms are the one responsible for this. Take, for example, if we bury cassava underneath water, what happens to the glucose in the cassava? then you have bacteria and some other microorganisms trying to get energy from the cassava, as it were. Let's say, okay, this is glucose, this is H12, O6. In this case, that's good. They're going to respire anaerobically. So what we're going to have, this is glucose. Now we're going to have C2H5OH, ethyl alcohol, or what we call ethanol. And that's actually an alcohol. Okay. In balancing this, okay, this two, okay, plus 2CO2, that's carbon dioxide. So the conversion of glucose to this ethanol, so that in most of the food we consume, when we say the food has fermented taste, it has a fermented taste, it simply means the glucose content, some of the glucose content, though in a very lower percentage now, has been converted into alcohol, in this case ethyl alcohol or ethanol. So this is a case of anaerobic respiration, and in the process at least 2 adenosine triphosphate or energy is released to the microorganism. But the point is this: there is nothing you can do to reverse this so that you get back your monosaccharide or sugar. No, it is not possible. This has happened, it has happened, and it is a chemical change. Talking about decay of substances, most especially by microorganisms as well. When substances decay, there is nothing you can actually do to reverse them back to what you have at the start. In most cases, fungi causes decay of substances. Let's assume we have leftover food. Suddenly, the leftover food begins to turn liquid. What is happening? What is causing the decay of that? Or let's say like bread. After some days, you begin to see a green substance, mucor, fungi on it. What is happening at that point is that fungi, which is a microorganism, is now begin to release enzymes into the organic matter so that they break it down, so that they cause the decay. So decay of substances is actually a chemical change. And then another one, talking about the burning of metals, magnesium to be precise, as you can see on your screen. When magnesium burns, it burns with a dazzling white flame, and white ash magnesium oxide is produced in the process. Okay, look at the equation here. When magnesium burns, recall that I said burning simply means something is combining with oxygen. In the case of magnesium, when it burns with a dazzling white flame. It burns with a dazzling white flame, and you can see that on your screen as well. So that in the end, you have magnesium, white ash magnesium oxide. There is nothing you can do to this white ash magnesium oxide to get back your magnesium and oxygen. No. Of course, we could talk other metals. If it were to be calcium, calcium burns with a brick red flame. Calcium bonds with a brick red flame. If this combines with oxygen, this is what you're going to have, okay? 2 calcium oxide. It burns with a brick red flame. If it were to be potassium, it burns with a purple or lilac flame. If it were to be sodium, it burns with a golden yellow flame. If it were to be copper, it burns with a blue green flame. And if it were to be lead, it burns with a blue flame. Now, the colors of these metals are what is we use for fireworks. Fireworks, it gives the coloration of the various metals when they burn. In the course of, let's say, events, celebrations, when you look at the sky and there are fireworks, the different colors, red, orange, yellow, white, are the colors of metals. Now, when these metals burn, the product they give, there is nothing you can actually do to reverse this. Another chemical change that we need to look at is slaking of lime. Slaking of lime. That is, when we say slaking of lime, we talk about addition of water to lime water. Addition of water to, when we talk about slaking of lime, we mean addition of water to quick lime. Quick lime is actually calcium oxide. That's quick lime. That's quick lime. So when I add water to my quick lime, this is what I'm going to have. I'm going to have calcium hydroxide. I'm going to have calcium hydroxide, slaking of lime. There is nothing I can do to this calcium hydroxide. It is not reversible. I cannot convert it back into quick lime and water. It is a permanent change which cannot be reversed. And with that, we have come to the end of this topic, talking about physical and chemical changes and the properties of materials or matter. So don't forget, subscribe, turn on the notification bell, and do share with your peers. From myself and the entire team here, it's bye for now.